Today we're going to go over exam 3 from General Chemistry 1 for fall of 2018. This is covering chapters 6 through 9, although we didn't cover all of chapter 9 in this case. So the first two pages are the multiple choice. I'm going to try and go through these and explain how we get to each answer in as efficient a manner as I can. Okay, question 1. So a single covalent bond contains blank electrons. Right? So every bond, whether sigma or pi or single or double or triple, each, let's say, line that we use to represent a bond, so if I have a carbon bound to another carbon, right? Each line that we use to represent a bond represents a pair of electrons, right? So a single covalent bond represents one pair of electrons. The weakest bond from the list below: single, double, triple, ionic, and then they're all of the same strength. Well, with respect to A, B, and C, right? With respect to bond strength, single bonds are weaker than double bonds, which are weaker than triple bonds, right? So triple bonds are the strongest, single bonds are the weakest. But even out of all those, covalent bonds are weaker than ionic bonds. If you take a look at the properties of the molecules, the melting points and boiling points, ionic compounds are by far have stronger interactions than covalent bonds do. So ionic bonds are always going to be stronger than covalent bonds, at least for everything that I've ever encountered and everything that you'll be dealing with in this course. Right? So ionic bonds are always going to be the strongest. Question 3 was a little bit trickier than I'd hoped it would be. I think that's just an issue of wording. But the question was asking which of the following is the least polar bond. Right? And I would have accepted either answers A and B in this case. But let's just talk about what it means to be a polar bond. Yeah, so I accepted either one of these in this case. But let's talk about what it means to be a polar bond. Right? For a polar bond, right, there is a difference. Right? There's a difference in electronegativity. And this is what we talked about in class with atoms playing tug of war with each other, right? When two atoms are bound together, they're going to play tug of war for the electrons that they use to make that bond. And whichever one wins the tug of war, right, is going to have a partial negative, and the other one's going to have a partial positive charge, right? So in this case, we have chlorine bound to fluorine, fluorine bound to hydrogen, fluorine bound to lithium, and two chlorines bound together. You have to know the top four, right? The top four most electronegative atoms, right? From increasing, right? It's chlorine, then nitrogen, then oxygen, and then fluorine, right? So fluorine's number 1, chlorine's number 4 in terms of electronegativity. The bigger the difference in electronegativity, the more polar a bond is going to be, right? The bigger the difference in electronegativity, the more polar a bond is going to be. So the closer in electronegativity or the less polar a bond is going to be. Right? So chlorine bound to fluorine is going to have it's going to be a polar bond, but it's not going to be nearly as polar as when fluorine is bound to hydrogen or fluorine is bound to lithium. Right? So that's what I was looking for here. Which one of these has the least difference in electronegativity is probably a better way of asking this question, right? But now, if we look at the case of, right, an atom bound to itself, right, you can't win tug of war if you're fighting with yourself, right? So for chlorine bound to chlorine, it would be a non-polar bond. It would be a completely covalent bond, not a polar bond at all, right? So I can understand where the confusion might have come in this case, and so I accepted either one, right? But to the point of polar bonds, you have to know electronegativities and the trends of electronegativities. Question 4. So using periodic trends, place the following in increasing ionic characters. So question 3 and question 4 are related, right? They're both asking about polar bonds and electronegativity and increasing ionic character, right? The bigger the difference in electronegativity, the bigger the difference in electronegativity, the closer to a ionic bond you get, right? So we have to know the relative electronegativities of the things here, right? Now, if you look at the periodic table, let me pause for a minute and pull up a periodic table. All right. So going back here for a second, right? We've got silicon bound to phosphorus, to chlorine, and to sulfur, right? So the silicon remains constant in all three of these compounds. Now, without looking at the periodic table, we should know that the chlorine, right, being the fourth most electronegative in the periodic table, the difference between silicon and chlorine is going to be there's going to be a large difference in electronegativity. So silicon bound to chlorine is going to be the most ionic character, right? It's going to be the most ionic. It's going to have the largest difference in electronegativity. So it's going to be the most ionic, right? So it should be at the end of our list. Now we have to look at phosphorus versus sulfur. So let's take a look at the periodic table, right? So here's silicon, right? Here's phosphorus right next to it, right? Here's sulfur, right? And here's chlorine, right? So on the periodic table, the closer the two atoms are together, the less difference there is in electronegativity. And what I mean is this, right? So when silicon is bound to phosphorus, there's not a great difference in electronegativity there, which means we have a more covalent bond, as opposed to silicon bound to sulfur, which is a little bit further away. So we have a more ionic bond in that. It's still a covalent bond, but it's more polar, right? It's closer to ionic. And then silicon bound to chlorine is going to be the most ionic in character. So the further away two atoms are in the periodic table, the more ionic it becomes. So really this was a question of knowing your trend for electronegativity, right? So silicon and phosphorus is least, right? And this is, and then the silicon bound to sulfur is, second, right? So in increasing ionic character, right, silicon bound to phosphorus is the least ionic, silicon bound to chlorine is the most ionic, and the sulfur one's in between, right? So B is going to be the answer in this case, right? Silicon bound to phosphorus is less ionic than silicon bound to sulfur, which is less ionic than silicon bound to chlorine, right? Increasing ionic character. All right, question 5. Choose the best Lewis structure for BeF2. Okay, so you got to draw the Lewis structure, and you got to go through and check to see what's going on, right? So back to our periodic table. Let me erase this stuff here. And we've got beryllium over here, and we've got fluorine over here, okay? So we have to look at the periodic table. We have to know how many valence electrons it has. Beryllium's got 2, and each of the fluorines has 7, right? So we're going to bring that information back in. Right, step 1, valence electrons. We've got 2 from the beryllium, plus 14, right, from the 2 fluorines. So a total of 16 valence electrons. Okay. You put the beryllium in the middle. Put the least electronegative in the middle. Bind it to 2 fluorines, okay? And then we fill in electrons from the outside in, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So we got 12 as lone pairs, right? And then 14 and 16, they're coming from our 2 bonds, okay? You go through and you check your formal charges, right? So you can use the circle method, you can use the formula method, right? Either way is just fine. And we find that we have 0 formal charges in all 3 of these, right? So this is going to be the answer for the best Lewis structure. If you go through and check your formal charge for any of the other ones in here, right, you're going to see that the formal charges aren't ideal, and in some cases we have over octets. In some cases we have, under octets. So this is the correct Lewis structure. Right? Now I'm not going to go through and tell you exactly why all the other ones are incorrect. You can go through and figure it out, and that'd be great practice. the point that I try to emphasize in class is there's a sequence and a step to drawing a Lewis structure. You start out with your valence electrons, right? That's step one. Step two, you draw your skeletal structure, right? Right? Where you connect everything to the central atom with single bonds. And step three is you fill in lone pairs, right? Lone pairs from most electronegative to least electronegative from the outside in, okay? You can go take a look at some of my other videos or the notes or the whatever you want. I explain this in quite a few different places, okay? So there is a sequence and a step that I ask you guys to follow when you're going through and doing your Lewis structures. And as long as you follow those steps, you're never going to get this wrong, right? The problem comes when you guys try to skip steps. And we'll talk a little bit later on pages 3 and 4 where a lot of the common mistakes happen on this exam, right? And we'll talk about how and what steps got skipped, okay? All right. Question 6. Draw the Lewis structure for NO2 and include any valence resonance structures, and which of the following statements is true, right? So we have to draw the Lewis structure for NO2. So NO2 is going to look like this. Right? And we draw a resonance structure, right? Remember, a resonance structure is where we move our pi bond around. We turn a lone pair into a pi bond and a pi bond into a lone pair, right? All right. Those are our two resonance structures. Now remember, this question is asking two things, right? One, can you draw a Lewis structure? And two, do you understand what a resonance structure is? Okay. So what does it mean to be a resonance structure? Well, a resonance structure means that both numbers 1 and 2 there exist simultaneously. Okay. Both structures 1 and 2 exist simultaneously. And so we don't have a single NO bond, right? We don't have just one NO bond and one NO2 double bond, right? Those with resonance structures, with the bonds moving around, what we actually have is a hybrid of those two, right? We have those two happening simultaneously, right? So here's what I mean. Let me put some colors in here. Let's make that one green. Okay, we'll make this one purple here, and then we'll make I think black will stand out, right? Okay, right. So we've got our green, our purple, and our black bond, right? There's two ways you can look at this, right? Two ways to get the answer for resonance structure is one, you can count, right, to see how many bonds there are spread out over how many locations. So let's do that first, right? So there's 1, 2 locations, right? There's 2 locations, right? There's 2 locations, and how many bonds are spread out over those 2 locations? Well, there's 3 bonds, right? The green, the purple, and the black. Right? The green, the purple, and the black, there's 3 bonds spread out over 2 locations. So 3 divided by 2 is what? 1.5. And that's what we mean by both of those exist simultaneously. All 3 of those bonds are existing between those 2 places there. Okay? So that's one way of getting to the correct answer. The other way of getting to the correct answer is looking at which bond actually moves, right? So we have the green and the purple. The green and the purple don't change. The black one changes. So we have one black bond spread out over 2 locations, right? So it really exists as half of a bond. The green and the purple exist as one bond, right? They don't move, but that one bond actually does move, the purple one, right? So we can get to 1.5 thinking about it in that way also, all right? But the thing to remember with resonance structures is that you have all those bonds spread out over the different locations. Now, when you get to something like organic chemistry, you're going to use resonance structures a lot, and it's a very important topic. So it's important to kind of sit here and think about this for a little bit and read through the notes and read through the chapter. But at the end of the day, you know, resonance structures all exist simultaneously. And so we start to see things like half bonds or third bonds or quarter bonds where we see a pi bond kind of hopping around in between different areas. All right. Question 7. So rank the following in decreasing bond length, right? Decreasing bond length from the central atom there. All right, so first things first, we should always draw Lewis structures, right? SiO, okay. CO2, there's that. And then CO3. Alrighty. So there are our 3 Lewis structures, right? So now we got to think, right? We got to think here. Decreasing bond length. That means we want the shortest bonds to be, at the end of our list, right? We want to figure out which one has the shortest bonds and which one has the longest bonds. Well, we got to think about this, right? If you take a look at the structures in green and purple, you need to notice that these have resonance, right? Right? Both of these have resonance structures. Well, how do you know? Well, take a look in the notes, right? We walked through this example, right, directly in class, right? We walked through this example directly in class there, right? So remember we talked about how we can push electrons around, right? We can drop a lone pair to make a bond, and we can turn a bond into a lone pair, right? To where we can make a resonance structure that would look like this. Right? And we can do the same thing over on this molecule here too, right? At the end of the day, right, just to clean this up here a little bit, at the end of the day, right, we go through and do our analysis again, right? We can draw, we have 4 bonds, right, 4 bonds over 3 locations, right? So here we have 1 1/3 bonds. If we go over here, right, we can draw 3 resonance structures because we have 3 equivalent oxygens, right? And again, we have 1 1/3 bonds. Okay, so 1 1/3 bonds here, 1 1/3 bonds here, okay? If we take a look at our buddy CO2, right, we don't have any resonance structures. We just have a carbon double bound to another oxygen, right? So here we have 2, right, a bond order of 2, a double bond. The more bonds you have, the shorter they are, right? So a double bond is shorter than a 1 1/3 bond, right? So the CO2 is going to be the shortest. Right, so you see we have 2 answers where they're the shortest over here, right? So we took care of our CO2. Now we've got to compare our CO3 to our SiO3. Well, they both have a bond order of 1 1/3. So what is different here? Well, the difference is what's in the middle, right? Here we've got a carbon, and here we've got a silicon, right? So not only does bond order affect distance, right, it's also the size of the atoms. Carbon has a smaller radius. Carbon has a smaller radius than silicon. So carbon will make a shorter bond than silicon will. Which means that our buddy over here, CO3, right, even though that has a bond order of 1 1/3, it's going to be a shorter 1 1/3 than SiO3 because of radius, right? So my answer here is going to be that one. You have to look at bond order, and you have to look at atomic radius, right? So radius and bond order are going to give you an answer for, telling us about bond length. SeCl4. Now this ended up being a problem with a problem which unfortunately a number of students missed, and I think it was just because we were going too fast through the exam here, right? So, to know the molecular geometry, you have to draw the Lewis structure, right? Selenium has 6 valence electrons. We have 4 chlorines that each have 7, so a total of 28. From there, for a total of 34 electrons, right? That's step 1, our valence electrons, okay? Step 2 is our skeletal structure. Least electronegative goes in the middle, that's selenium. We connect to our 4 chlorines, okay? There's our skeletal structure. Step 3, lone pairs, okay? Start with our most electronegative, work our way in, right? All right, so how many electrons have we used so far, right? We used, let me switch colors here, right? We used 2, 4, 6, 8, right? Then 10, 12, 14, 16, 18, right? Right, we get all the way through here, right? Right, so 2, 4, 6, 8, 9, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, right? So we only use 32 electrons to draw this structure. But, right, we need 34. So where is that 34th electron going to go? Or that pair of electrons to make 34 going to go? Well, it's going to go around our central atom. Right? It's going to go around our central atom. So we're going to put another lone pair here. Okay. So now we've used all 34. Now to get our molecular geometry, right, we need to know how many total things we have, right? 1, 2, 3, 4, 5, right? We have 5 what we called things, right? Electron domains. We have 5 things that come from 4 atoms and 1 lone pair, right? 4 atoms and 1 lone pair. That's going to get us our seesaw molecular geometry, okay? 5 total things for an electron pair geometry of trigonal bipyramidal, with molecular geometry of seesaw. Got to draw your Lewis structure and have to know your geometries, okay? Question 9, remember this one had that typo, right? So there were 2 answers that were accepted here. Which ones are not allowed? Well, we can quickly look at some stuff here, right? M sub s, they're all plus 1/2 and minus 1/2, right? There is no problems with M sub s over there. So we don't have to worry about M sub s giving us any clues. So let's take a look, right? Question A, we have n equal 3, we have L equal 3, and M sub L equals 0, right? Well, if n equals 3, right? If n equals 3, L can only be equal to 0, right? 1 or 2. But here in this case, we have L equal 3, right? N cannot equal, N cannot equal L. The maximum for L is N minus 1, right? So A is one of our incorrect sets, okay? We move on to B. We have n equal 4 and L equal 3. So far, so good, right? L can equal 3 if n equals 4. M sub L is equal to 2. And so n equals 4, L equals 3. So far, so good. If L equals 3, M sub L is equal to, can equal negative 3, negative 2, negative 1, 0, 1, 2, or 3, right? And we have a value of M sub L equal to 2, which is part of our valid set over here. So no problems with B. No problems with C either. And we get down to D, where we have n equal 5 and L equal negative 4, right? L can never equal a negative number, right? No such thing. So those are the 2 acceptable answers there. So how do we answer this problem? You have to know what the limits are, right? N can equal anything, right? N can equal anything from 1 to infinity, right? L is equal to 0 all the way up to n minus 1. M sub L is equal to plus L. Sorry, let me write this a little bit neater. From plus L to minus L, okay? You have to know what your limits are, and that's how you answer this question. All right, so that is the end of the multiple choice. In the next set of videos, we'll move through the Lewis structures that we have to draw on the next pages. So I will zoom out to show you guys the answers. And we will pick it up on the next video.